Eighth graders, I hope you're having a wonderful week. This is Mr. Whited, and this week I wanted to record a video on electromagnetic waves and the electromagnetic spectrum specifically. So let's get started. So thank you for those who turned in their student work or turned in the anatomy project last week. They all looked really good. I appreciate it. Thank you for working hard. Make sure you hold on to those, use them as reference. Those are great ways to look at, use as notes and things like that, and to refer back to as we go forward. If you didn't finish, that's okay. Just keep working on it. Complete all work and submit it to the Anatomy of Wave assignment located in Canvas. 3D is optional and for extra credit. I did get a few 3D submissions and they looked amazing. I think that's a fun little project you can do at home, and you can use whatever materials you have. Just take your drawing and make it 3D. Here's some examples of some of the work I received. Now, I couldn't put everybody's work up there, but everything I did receive was good. So I'm in the process of grading them, and you should be receiving grades, this today or tomorrow, or this week, depending on when you watch this video, right? So here's some submissions, and I'm going to post this PowerPoint. So if you want to go back and refer back to some of these drawings, they all came out really well. Here's some more. All right, so let's just kind of do a really quick review on what we know so far. So here's a transverse wave. And a transverse wave, here are the different parts. Remember, a transverse wave, it looks like a little roller coaster, kind of goes up and down. And it has a crest, it has a trough, it has a rest line, which is right here. And we measure the wavelength from crest to crest, or it can be from trough to trough. If this continued on and we had the trough over there, you could measure it from here to here. And frequency, which I don't have listed here, and I noticed when I looked at some of the definitions, sometimes the online definitions, when you Google it, they're kind of vague. But in specifics to waves, a frequency is the amount of times a wavelength goes through a given point in a measured amount of time. So it's a way of measuring how fast this wave is traveling. Alrighty, so let's look at a longitudinal wave. Now this is a wave in which the wave moves in the same direction as displacement of the medium. Okay, well remember, longitudinal waves are mechanical waves, which means that they require a medium. More commonly, we see them with sound. Sound is a type of longitudinal wave, and they have a compression and they have a compression, and they kind of move, they kind of wiggle back and forth like a little snake, right? And the matter that the wave is traveling through tends to kind of bob back and forth. You can go back to my previous PowerPoints if you want to see some of those GIFs, right? And the different parts, you've got compression and compressions. That's where the matter is kind of compressed together, and that's how we measure one wavelength. And then we've got a rarefaction. Rarefaction is where they're kind of spread apart right here. And this is like a slinky, right? It's just a way of representing what a longitudinal wave. A slinky is not a longitudinal wave, but it's just a way of representing what it might look like. So if you took a slinky and you had two people hold it on both ends, and you could try this at home, you can kind of push it back and forth, and you can see where the slinky kind of compresses at certain parts and then it expands at certain parts. And that would be a good way of representing a longitudinal wave. So this week we're going to focus mainly on electromagnetic waves. And remember, electromagnetic waves are always going to be a transverse wave. So they're going to kind of have this up and down roller coaster motion. And this is an example of an electromagnetic wave that I've shown in my previous PowerPoints. And it's electromagnetic because it has a electric field, which is the red. So that's one transverse wave, is this electric field. And then it has a magnetic field, which is 90 degrees to the electric field, perpendicular. So it kind of goes sideways. And this is a wave that would be like light. It travels through space from sun to the earth, and it's just a way of representing. Of course, this isn't exactly what it looks like. This is just a way for scientists to kind of give a excuse me, to show what it looks like, to kind of give you a visual. So we're going to look at the spectrum. So the electromagnetic waves, they come on a spectrum, which is just basically It's a range of the waves. And there's a whole spectrum of them. And that's your goal this week, is to focus on the spectrum and what is the spectrum trying to show us. So I'm going to go through and just kind of talk you through it, the different types of waves in our spectrum. What can we see, and what does all these numbers mean? Because there's a lot of stuff going on in this little picture right here. All right, so as you notice from left to right, so as I start over here, if you look at just the wave, we can see that this is a transverse wave, right? It goes up and down, it has a crest and a trough. And look what's happening to the wavelength as we go from left to right. So the wavelength is from crest to crest. This is why it was so important to kind of get you to understand the anatomy of the wave in the last couple weeks. So here's a wavelength. Here's a wavelength. All right, as we go further and further to the right, what is happening to that wavelength? Well, you might notice that it goes from longer. So here's wavelength in meters, longer to shorter. So as we go from radio waves all the way to gamma rays, wavelength decreases. It goes from a longer wave to a shorter wave. On the flip side, frequency, which is the amount of wavelengths that travel through a given point, it's very low on the left side and gets very high on the right side. Well, what does that mean? Well, it means that as waves travel from the left to the right, they are increasingly bigger, much bigger, and I'm going to show you an image in a second which shows that radio waves are really big, right? Almost as big as mountains or skyscrapers, the big buildings. This is why radio waves can travel long distances, and we can hear the radio from, say, Atlanta, right? We can hear the radio station, to all the way to gamma rays, which are very small, but they travel very fast. So slower, bigger, and as we go to the right, smaller, but much faster. And these from ultraviolet, and there's a T missing there for some reason, but from ultraviolet all the way X-rays and gamma rays, these are the ones that can start to hurt you. They actually can damage your body, but they're so small that you have to be within a very specific given period in order to be damaged by these particular waves. Okay, so this is very important to understand. So this is a big thing to understand this week. Wavelength goes from bigger, longer, to shorter as you go from left to right, and the frequency increases as you go from left to right. And right here in the middle, we have what's called visible light. This is actually what we can see as humans. All these waves are on this, they're all electromagnetic waves, including what we consider to be light. But we only see a very small portion of the spectrum, and that's what we see right here. Now, there's also numbers involved here, and these are important too as well. Remember exponents from math? What happens when you have a bigger exponent, right? So we're looking at wavelengths. So we got 10 to the second, right, which is 10 times 10, 100 meters. And then as it goes down, look, it gets into negatives, and negatives are very small numbers, right? If you remember scientific notation, you take your decimal, move it to the left, you get a very small number. And then here we have 10 to the negative 13, right? If we take that number and move it 13 places to the left, you would have a 0.0000, whatever the number may be, a very, very small number. So that's what it's trying to show you. Wavelength goes from longer, bigger, to much smaller as you go from left to right. And then frequency, look, 10 to the 6, and then as you go all the way up, 10 to the 21st power. So you can see that frequency gets increasingly bigger as you go forward. Here's an image from NASA's website, which is the exact same thing, but it shows you all the different uses for these waves, which I think is important. We're going to look at too. But this also shows you the length. So here we have radio waves. This is the length of a football field. Then it gets to microwaves, approximately somewhere in between the width of a baseball, thickness of a paper, the width of a water molecule, the size of an atomic nuclei, right? So very, very, very small. All right, so now I'm going to go through each one really quick and just kind of give you a brief overview. So the first one we looked at was radio waves. So very big wavelengths, very small frequencies. So largest wavelength, lowest frequency. We use these quite often for, as you might guess, radio, television, and radar signals. Cell phone uses cell phones actually use radio waves, but they fall kind of in between radio waves and microwaves. So you'll see kind of different people argue, well, cell phones use radio waves, cell phones use microwaves. They kind of use somewhere in between, but I put it in here because it's closer. One more thing about radio waves. You ever notice that you tune into a certain frequency? So for instance, 94 point whatever FM, that it has to do with the frequency of the wave. So as you go through the different radio stations, they have different frequencies. Remember, it's the amount of wavelengths that travel through a given point in a certain amount of time. I think that's interesting that, just to kind of refer that back to radio waves. All right, and then we have microwaves. As you might have guessed, microwaves are used in microwaves. But we also use microwaves for wireless communications too as well, which is very common. Microwaves in the ovens mainly are used to heat things up, and that's kind of what's happening with those waves. Those waves are kind of hitting the water within the material, and it actually starts to heat it up, or it hits the material itself and then transforms into heat energy. The next one is infrared. Now, infrared is, you may have seen them like in these little infrared cameras. Uh, that's where you'll commonly see that. The infrared heaters. We also use infrared in weather, right, to kind of predict the strength of a storm. Those kind of reds, yellows, and greens that you see are all from infrared. We cannot see infrared, but you can feel them as heat. And all objects give off infrared. If it has, most objects give off some form of infrared energy. Okay, and this is the visible spectrum. This is the actual spectrum that we can actually see it with the human eye. So it's amazing to think that from on the left side we have radio waves, infrared, and microwaves right in between. We can't see those. We can't see ultraviolet, we can't see X-rays, we can't see gamma rays, but we can see this little visible spectrum that's in between infrared and ultraviolet. And there are several colors, or there are various colors that we can see. So red is where it starts on the left. Red has the highest wavelength out of the colors, lowest frequency, which means it's the lowest energy. Then it goes orange, yellow, green, blue, indigo, and violet. Violet being the highest frequency, lowest wavelength. And that's what this little box right here is trying to show you, is that even within this little spectrum, right, there's a spectrum from left to right. So as it goes from left to right, you go from a higher wavelength to a lower wavelength, lower frequency to a higher frequency, which means higher energy. So violet actually has the highest energy. Red has the lowest energy out of the visible spectrum. And then here is a rainbow, and you can see those colors in that rainbow. So it's amazing. You can see it in nature too as well, right? So it starts with red, orange, yellow, green, blue, indigo, and violet. And then you have UV rays. These are the rays, this is where the electromagnetic waves can actually begin to hurt you. That's why they can cause sunburn. We also use them in medical. We use them right now, I'm sure, quite a bit to sanitize medical things and to kill bacteria. And then you've got X-rays. These are very short wavelengths, high frequency. So that's why they put little protective things around you to keep you protected. So if you ever go to the dentist to get your X-rays of your teeth, or maybe you broke a bone in your hand and they need to do an X-ray, right? They have to protect you because X-rays can damage the body, but they also can be very beneficial for us to use them in medicine and things like that. And then our last one are gamma rays. Gamma rays are the shortest wavelengths and they have the highest frequency, which means they have the highest energy. Uh, Given off during nuclear reactions, we use them quite a bit in medicine for cancer treatment, and we see them quite often in astronomy in measuring when we have stars that are exploding, things like that. They give off gamma rays that travel through space that we can detect here on Earth. Very high energy, but remember, the wavelengths are as small as basically an atom. So you have to be in that proximity to even be affected by it. All right, so that's the electromagnetic spectrum this week. Please email with me with any questions. I know this was fast, but please email me if you have any questions, and I hope everybody has a great week. Thanks.